Now let's take a look at how to model this problem in ABAQUS. So here we have a dog bone specimen, and the question asks us to use a plastic material properties defined here, and we need to use plane stress to model this problem, and the Young's modulus of this part is 200,000 megapascal, and the Poisson's ratio is 0.3. So the geometry has the following dimensions. So the length is 450, and the height is 150. So in order to model this problem, if we take a look at this problem, we can find it's this part is symmetric around this plane, and it's also symmetric around this plane. So we can use symmetric boundary conditions to simplify this problem. So we can just take a quarter of this specimen and to analyze it. So this way we can save we can simplify the computational complexity and have a refined mesh over a quarter of this part. So in order to model this quarter, so we need to find the coordinates for this quarter. So for the first point here, we can define it as 0, 0. And next point is here. The coordinate is half of the length is 225 and 0. And next point is here. So we have 225 for the x coordinate, and for the y coordinate, it's equal to the half of the head. It's equal to 75. And then for the next point is here. So for this, the coordinate of this point is equal to, so the half of this length, which is 100, plus the dimension of the radius of this fillet. So it's 150. So the x coordinate is 150, and the y coordinate is 75. So here for this part, we have a fillet structure. So we can just ignore it here. And then in ABAQUS, we can use create a fillet tool to change this right angle to this fillet. So we just need to find the coordinate for this point. So the coordinate for this point is 150 and half of the height of this part. So it's 25. And then the coordinate for this point is 0 and 25. Now we have the coordinates of all points that we need to create this structure. Now let's create a part in ABAQUS. So here, let's call it dog bone. And it's we are going to use the plane stress. So it's a 2D structure and deformable. So here, so we can put since the length of this structure is 450, so we can put 450 here, so that we can make sure that the sketch is within the grid. So click continue, and then we click this structure. And the first point is 0, 0, and then we hit enter. And then the next point is 225, 0. 225, 0, and hit enter. And then the next point is 225 and 75. 225 and 75. And then next point is 150 and 75. 150 and 75. And then next point is 150, 25. 150, 25. And then the next point is 0, 20, 25. 0, 25. And then we close the geometry. Here we have the sketch, and then we need to change this to a fillet. So we use create fillet. We use this function in ABAQUS. It's called create fillet. So we click this one, and then the radius is 50, so we put 50, and then we need to hit the middle mouse button. Oh, sorry, we need to hit enter, and then we need to select the first entity. So it has to be the adjacent lines. So we are going to create a fillet for this corner. So we need the first entity has to be this line. And then the second entity has to be this line. So here we have a fillet here. Now we have created a quarter of the structure. And then we can hit the middle mouse button and click down. Now we have a part. And then we need to create material properties. So for material properties, remember we are using plastic behavior of this material property. So, and here, so I've copied this data. So I've copied this data from this question to the Excel, because here we have engineering strain and engineering stress. So in the software, we need to turn it into true stress and strain. So I copied the data here. So in order to convert engineering strain and engineering stress, we use the Excel. Here the true strain is equal to the lateral log of 1 plus engineering strain. And the true stress is equal to the engineering stress times 1 plus engineering strain. So we have this formula here. The true stress is equal to, this is equal to the engineering stress times 1 plus engineering strain. And the true strain is equal to the lateral log of this. This is equal to 1 plus engineering strain. So here we have a true strain and engineering strain. And then we drag it all the way here. So now we converted the engineering strain stress relationship to true stress stress-strain relationship. And we also need to calculate plastic strain, because the plastic behavior is defined by yield strain and yield stress and plastic strain. So here, the plastic strain is equal to the total true strain minus the true stress divided by its Young's modulus is 200,000. And then we drag this all the way here. So here you can see that for the first 3 rows, we have a lactive plastic strain. So it's negligible because it's in the elastic region. So for the first 3 data points, we are in the elastic region, and from here to here, we are in the plastic region. Now, let's take a look at how to define both elastic and plastic behavior of this material. So we follow the same step. We create a material, and previously we defined the elasticity for the material. And for this plastic material, we have both elasticity parameters and plastic parameters. So in order to define the elastic behavior, so it's exactly the same as what we did before. So we put Young's modulus here, which is 200,000 and Poisson ratio. Now this material has elastic behavior, and then we need to go to the plasticity and define plastic behavior. So you can see the plastic behavior is defined by the tabular data. So here is the yield stress, here is the plastic strain. So the yield stress, so we can see here, this is the plastic region. The first 3 data points is in elastic region, and for the 4th one, we have some plastic strain. So we can define our yield stress as 400.8. So from here, so this is our yield stress. And then if the strain is greater than, if the stress is greater than this value, we will have some plastic strain. So there are 2 ways to input this data. We can just do it manually, like we can put 400.8 and 0. This is one way. And for the next data point, we can just right click and insert a row after, and then we can do this. We can input it manually. Or we can just copy this, copy and paste it the data here, Control V. Now we have this. So there is one thing that we need to be very careful, is that for the first data point we used to define plastic behavior, the plastic strain has to be 0. If you put 0.0000001, then you will have an error when you run this use this material. So this has to be 0. And now we have both elastic and plastic behavior, and we click OK. And then the procedure will be exactly the same as what we did before. So we create a cross section, and we assign the material with plastic behavior to this section. Click OK, and then we assign the section to this structure and click done. So we select section 1 and click OK. Now we have successfully assigned the material property. Next part is the mesh. So for this part is here we have a fillet. So if we mesh it previous, like what we did previously, so we can just input a global size, maybe put it 20 and apply OK. Or we can put it 10 if we want to refine the mesh, and click apply. And then here we click mesh it, yes. So we can see here for this part we have both quadrilateral element and triangular element. And this for these elements, it's a little bit we have a little bit distortion here, which is usually not good. So what we can do here, so we can go to the mesh control and use quad and use this medial axis. So using this option can really help you minimize the mesh distortion. So now we have meshed it successfully. So next we need to create an instance. So we go to the create instance and click OK. We only have one part. And then we create a step. So let's call it step 1 and static general. So here, as we are dealing with nonlinear material property, so we have to turn it on. And here is the incrementation. So if you remember what we discussed in last week's lecture, we know that the software apply nodes for nonlinear problems by incrementation. So here you can see the first parameter is maximum number of increments. So if we put 100, it means the software will try to apply the entire load within 100 increments. And here is the increment size. So the initial increment size is 1. This is default, and you can put it as 0.1. Or this is the initial value, and the software will adjust this value based on if the initial step succeeds or not. And this is your minimum increment. So if the increment is less than this value, then the software would stop running. This is the minimum increment that the software would try. And this is the maximum increment. And within each increment, so the software is going to use the Newton-Raphson method to find the solution. Let's click OK. And now we can add boundary conditions. So for the boundary conditions, we need to apply symmetrical boundary conditions. So for the first boundary conditions, so we go to symmetry, anti-symmetry, and encastre. And so we select this plane and click done. So for this plane, it's symmetric around this plane, right? So if it's symmetric around this plane, so this plane will only have displacement around U2. So for this plane, its normal direction is the y. So it's a y symmetry. So we need to use the y symmetry because any loads on this point will have a displacement of 0 along y direction, right? So u2 is 0. And any in-plane rotation, so which is means the rotation around the x-axis and the z-axis is equal to 0. So for this plane, we are going to apply y symmetry. So, and we also need to create another symmetric boundary condition. So for this plane. So for this plane, it's a x symmetry because its normal direction is the x-axis. And we have a displacement around along x-axis is equal to 0. So u1 is equal to 0. And any in-plane rotation, which is ur2 and ur3 is equal to 0. And here we have a pressure for the load. We have a pressure of 2000 megapascal. So for load, so we are going to not a concentrated load. So it's a pressure. So pressure. So we select a surface here and click down. So if you put 2000 Newton, so the pressure is going to pointing left because this is the pressure. So based on this question, the pressure has to point to the right. So we change it to negative 2000. Click OK. Now the direction is correct. And then we can create a job. Dog bone example. Okay. And click OK. And then we can submit job. Here we can see the file is error-free. So the analysis input file process completed successfully. So, however, the analysis has been terminated due to the previous errors. So it says the time increment required is less than the minimum specified. So let's check this, go to the monitor. So we can see here, for the last increment, it's 1 times 10 to the power of negative 35. So it's smaller than what we defined in the step. So here is the minimum increment that we defined is 1 times 10 to the power of negative 5. Because the last increment is smaller than the predefined value, then the software terminates the analysis. So if we take a look at the increment that the software applied to this for this problem, we can see that for the first try, the software tried with 1. So the software applied the entire load pressure, which is 2000 megapascal. And then it was unsuccessful. Then the software reduced the increment to 0.25. And then it's unsuccessful. And then the software reduced the increment to 0.0625. And then it was successful. Then the software continued using this time increment, and then it was successful, and then the software continued using this increment, and it was unsuccessful. Then the software reduced the increment again, and then it was unsuccessful. So the software reduced the time increment again, and it was successful, and so on and so forth, and all the way to this value, and the last value is smaller than our predefined value. That's why the software terminates the analysis. Now let's check the stress and find out why the software terminates this analysis. So we go to the result, and let's check the stress. So this is 1 Mises stress, and we can see here the 1 Mises stress, or we can just, because this is because this structure is under uniaxial load, so we can just check as 1,1. It should be exactly the same as 1 Mises stress. So here we can see for these elements, the S11 is 937.6, and it fails at this point. Why? So this is because the last plastic yield stress that we defined here is 937.25. So if you check, if you go to the tool query and check the stress, this is S11 for these points. You can see here the stress is exactly the maximum stress that we defined for plastic string, and similar here. And for this one, it's a little bit lower. But because these two elements has reached the maximum stress we defined for plastic string, then the software will terminate the job. So in order to make sure that your job can finish the entire load that you applied, so here you can just reduce the load so that you can finish the entire load step from 0 to 1. But this doesn't mean your model is wrong. So this is very important. So if your analysis can't finish the increment from 0 to 1, it doesn't mean your model is wrong. It just means sometimes the model can't take that much of the load. But your results from let's check the monitor here. So, but your results from 0 and all the way to 0.13597 is still valid. So next I'm going to show you how to plot stress versus the string relationship. So if you want to use the built-in plot function, so you can just go to XY data and create. So we go to ODB file, field output, and click continue. So here you can select here we can select the string. This is a logarithmic string because we use the nonlinear geometry option. So we are interested in LE11, so I can just tick this one. And this is the plastic string. So this LE11 is the total string. It has two components, elastic string and plastic string. So you can also check it from here. So if you go to the logarithmic string and LE11, so you can see if you check the value, so you can see for the integration points here we have 0.1397. So it's this value. This is our total string. So if you switch it to plastic string, yes, and check this value, you can find it's 0.135. So it's our plastic string. Okay, now let's plot the strain and stress curves. So we can check the total strain, which is LE11, and the stress S11, and then we need to pick an element. So I'm going to pick this one because usually this one reaches the maximum stress first. So we click this element. So we selected this element, and here you can use the built-in plot function. So you can click plot. So you can see here we have this red curve is the relationship between the logarithmic string with respect to the time steps. And this blue curve represents the stress S11 with respect to the time. What if we want to plot strain versus the stress? So usually I like to export this data to Excel and plot them. So let's do that. And we click, so you need to click Save Data and click OK. And then you can see here your requested XY data extraction has been created. And then we go to Report XY. And then you can see we have our stress at integration point 1. And here we have the stress at integration point 1. So let's hold Shift and select both of them. And then we check, we limit, we can limit based on your own preference. It doesn't matter. So I'll call it stress string text. And then click OK. So you can see we have created a txt file. So it's usually in the C temp file if you didn't if you don't change the path. And this is our data. So let's open it in Excel. Open, browse, and so it's in temp. Okay, here. So we use this to divide this divide each columns. And next, so we can use space and click next and finish. So this is our, so the first is our string, and then this is our stress. So this is our string, and this is our stress, and this is our time step. So this is the increments. So if we want to plot the relationship between the stress and the string, then let's copy this data to this. And this is the string, and this is the stress. So let's plot it here. This is our curve. This is a curve from the software, stress-string relationship from the software. So let's compare with it with the material stress-string relationship. So this is our string, and this is our stress. So we can just select, we can just add data. It's called choose string stress relationship. This is X, this is Y. So the blue one is the data from the software, and this one is the data from, this is our input material data. So we can see it's exactly the same except for this region. Why? This is because if we take a look at this, let's just delete this first so you can see why. So here we can see the software used a relatively large increment from here to here. That's why we missed these details. If we decrease the increment manually, we will find an exact curve as what we have inputted in the software.